let's see these derivatives in action. Here we see g of x is equal to the arc cosine of x, and we're to take the derivative and simplify if we can. I notice that what we have is a composition where the outside function is the arc cosine of x, and the inside function is the square root of x. Using the chain rule, we're first going to take the derivative of the outside function. The derivative of the arc cosine function is negative 1 over the square root of 1 minus the argument squared. The derivative of the inside function, we'll fill that argument in, by the way, in just a minute. The derivative of the inside function, since the inside function is the square root of x, is 1 over 2 times the square root of x. We're using the power rule. Remember, the square root of x is equal to x to the 1/2. Now remember, when we apply the chain rule, we don't change what's inside the argument. And so our denominator is the square root of 1 minus the square root of x squared. Simplify where possible. G prime of x is equal to negative 1 over the 2 square root of x times the square root of 1 minus x. Next up, same instructions. Our function is y equals the inverse cosine of the inverse sine of t. Well, the outside function is the inverse cosine. The inside function is the inverse sine of t. I'd like for you to pause the video and see if you can find this derivative and simplify. Well, it's not really going to simplify, but go ahead and pause it now. So how'd we do? The derivative of the inverse cosine function is negative 1 over the square root of 1 minus the argument squared. The argument is the inverse sine of t, and the derivative of that inside function is 1 over the square root of 1 minus t squared. This doesn't really simplify, but we can write this as a single fraction with the denominator. So it's negative 1 over the square root of 1 minus the inverse sine of t. And here I have to use squared. Here I have to use parentheses for the squared. Oh, not for the t, because I've already used the inverse sine function, right? And that's where I would put the exponent if it were, say, a sine function. So I don't get to do that. Anyway, 1 over the negative 1 over the square root of 1 minus the inverse sine of t squared times the square root of 1 minus t squared. I wrote y squared. That should be y prime. There it is. Next up, same instructions. R of t is equal to the arc sine of 1 over t. Again, pause the video, see what you can do with this. Now, I didn't get very far here because there are subtleties here that I wanted to go over with you. First, the derivative of the arc sine function is 1 over the square root of 1 minus the argument squared. The argument squared is 1 over t squared. Times the derivative of the inside function 1 over t. We are using the power rule, and so we have times negative 1 over t squared. I want to make a note right now that I'm going to refer to in a little while. The denominator here is the square root of 1 minus 1 over t squared. And then the factor here is negative 1 over t squared. The square root in the denominator has to be positive. 1 over t squared has to be positive. And so with this minus sign out here, this result has to be negative. Now we're going to return to that idea down the road. For now, let's continue simplifying our expression. I have a complex fraction here. See, I have 1 over t squared inside of a square root that's in a denominator. And so I'd like to fix that. So I'm going to pull the negative out front and then rewrite the denominator, the square root of 1 minus 1 over t squared times. Now I want to multiply t squared into that denominator, but in order to do so, it has to look like the square root of t to the fourth. See, you agree that the square root of t to the fourth is t squared. and now I have square root times the square root. Now I can multiply and actually distribute into that square root. So I get r prime of t is equal to, whoops, that's negative, negative 1 over the square root of t to the fourth minus t squared. And negative 1 over, so I can square root inside of the, I can factor inside of the square root a t squared. And I'm left with t squared minus 1. Now you may recall that the square root of x squared is equal to the absolute value of x. And so when I pull t squared out of that square root in the denominator, I have to remember the absolute value. And so I get as my answer r prime of t is equal to negative 1 over absolute value of t times the square root of t squared minus 1. Now that's the final answer. I would like to talk a little bit, though, about this absolute value. This is something that a lot of us may have overlooked if we had gotten this far. But let's go back to this idea when we first took the derivative that the expression is going to evaluate only to a negative number. That'll be true whether t is positive or negative. And in our original expression, r of t is equal to arc sine of 1 over t, t could be positive or negative. So here when we've taken r prime and we have negative 1 over the absolute value of t times the square root of t squared minus 1, without those absolute values, if t happened to be negative, then with this negative factor out front, this would evaluate to a positive number. Now it's not a problem if a derivative is positive, that's totally fine. It is a problem though if an expression that could only have been negative turns out to be an expression that could be positive. And you can see that we have preserved the minus sign in the square roots throughout the process. So up until this very last step, the answer would have had to have been negative. It would have to evaluate to a negative number. Once we reintroduce these absolute values now, this result can no longer be positive because with an only positive denominator and a negative out front, this would once again have to be a negative value for any value of t.